about 2 minutes to set this up. Okay, now is it? I love that we are the testers for these microphones. So I'd like to ask the AV people to turn off the video there. Take me about 1 minute to set things up here. Because this is actually in the nature of a pep talk. And it's an optimistic pep talk about software, and it's based on the work of many people here. I should mention that many of my heroes are in this room, and not just the people who got the Turing Awards, but some of the colleagues I've worked with over the years are my heroes. I think we wind up making ecologies when we're actually trying to do things. This has sometimes been mentioned, and these ecologies are critical because they actually require a wide variety of different talents. I've always felt that Turing exemplified a wide variety of talents inside himself, which is pretty darn amazing. I probably forgot something, but okay, let's start here. So this pep talk is about the Turing Tarpit and what we might do with it and about it. And I don't know where I was a big fan of Al Perlis. He's a fantastic guy. He was the first Turing Award winner. And early on, he said, beware of the Turing Tarpit, where everything is possible, but nothing is easy. And what's interesting about he was talking about programming languages, but in fact, this is true of the computer itself. That's the problem. It's got all these wonderful degrees of freedom, and we have to glorify in those because that's what makes it the most interesting machine that anybody's ever invented. And of course, the problem here is, oops, and fallen and perish. Now, I did a little research on tar pits, and I could not find anywhere that any humans were ever found in a tar pit that were not put there specifically as a ritual burial. So it seems like humans are a lot smarter than sloths. Sometimes you never can tell, but in fact, it looks like humans were pretty good at avoiding the tar pit. But we created a different kind. We realized, oh, there are all these hydrocarbons and fossil fuels, and we wind up with this. And this and one of the slums in Rio de Janeiro are my two favorite pictures of what I think of as software today. And the problem is we can't see them. We can only see 30 or 40 lines of code at a time. And there's this enormous festering whatever it is. And so this goes from whoops to a yikes. And the tendency we have, especially in this country, is to beat everything to death with a club. And what happens is the sub-goals become the goals. So at some point, just building refineries become the goals, where really what we wanted is energy. And it happens that 67% of fossil fuels are burnt to make electricity. And, well, if we want electricity, there are other ways of doing it. For instance, photosynthesis is pretty nice. I used to be a biologist, and what happens is through a beautiful series of chemical reactions and some physical pathways, it's pretty darn efficient at getting electrons, and electrons are what we want. So we get a yay on that, and there are a lot of organisms that do this, and the ones that don't feed on the ones that do, and it happens that the metabolism, basal metabolism in all living cells is somewhat similar, and it's a looking at it from the energetic standpoint, it's really about just transferring electrons around. And so there are a lot of electrons there. And in fact, recently it was discovered that many bacteria extend microtubules between each other, not for the purposes of sex, but for the purpose of exchanging electrons. Isn't that incredible? So they can get a kind of a feeding from each other they share. It's a socialized electrons. And because there are so many of these there, Adam Arkin, one of my favorite engineers who's also a biologist, says, hey, just stick the right things into the ground anywhere on the earth, including the Sahara Desert, and you've got a fuel cell made out of living microbes that are just happen to be there by the billions and trillions. And so, in fact, you can, out of pretty much any bucket of dirt that you get outside, you can run a 60-watt bulb just by having the right kinds of things that you stick in there. It doesn't require any additional power. And this is kind of a metaphor for, I think, what we should be thinking about in software. We have to think about what it is that we actually want to do, and I don't think our main goal is writing millions of lines of code. What we want it is to do something. So we've heard this in various ways today, but I like this idea of let's try science and math. Let's not beat it to death. And idea number 2 here is this distinction between tactics and strategies when we're building things. And tactical stuff is usually pretty incremental and somewhat similar to where you were. So bricks lead to piles and stacks, and if you scale them up, you get pyramids and walls. And they have a certain simplicity to them. Anybody can learn how to be a bricklayer. And so this has a lot going for it. It's very transferable and so forth. But it has some limitations, and so there's a strategic direction we could go, which is before we build things out of the materials, let's think of things we can make out of the materials that will be new materials. So in architecture, let's make some arches. That's where the term came from. And these things are incredibly efficient. The Romans made such good cement, aluminum silicates plus compaction, that many of these structures built thousands of years ago still survive today. If you've been in the Pantheon, it looks like it was built yesterday instead of 2,000 years ago. And in fact, it looks like it was made out of granite rather than the best reinforced concrete anybody has ever made. By the way, the frost giants in the Wagner operas came out of the inability of the Goths and the Visigoths to tear down these aqueducts in the Dark Ages. They concluded only giants could have built them. But in fact, it was just people like us with some technique. And the same thing is true in computers. Our building block is a comparison. We could call it the Sheffer stroke if you want. And again, we can go tactically in calculators. We can add a strategic element, the stored program. I love Jacquard looms. And this notion of storage models of computing is recapitulated through many of our languages. And the predominant amount of programming today, despite some fringe areas, is actually done using this storage model in a wide variety of forms, including so-called object-oriented languages. So this is kind of the general thing you find today. Most universities train towards these. And so we're talking about Turing. Really interesting idea is this brick idea is, yeah, you can program a computer to make something that's like the computer you're on, but you can also make it do something, a computer that is very different from the computer it's on. And the first one of these that I ever saw was Ivan Sutherland's Sketchpad. And it was definitely a computer. It was programmable. It wasn't programmable like any other computer had ever been. And it was completely different than the enormous TX2 computer that it ran on. And one way of thinking about it, and Ed Feigenbaum blazed the trail here, is that a lot of computing today is done in terms of hows. And as far back as 50 and 60 years ago, people were already starting about, can't we just program in terms of what's? Another one was John McCarthy. whose early paper on the advice taker, an intelligent terminal agent that you could give advice to that could deal with things in common sense terms. Lisp was actually invented to be a programming language to make that. That was an early idea. And of course, Marvin Minsky and Ed Feigenbaum and so forth have talked about intelligent systems as terminal agents. I'm going to focus not so much on AI here, but just this notion of what do we get if we can find ways to think in terms of what's. And Marvin called this semantic information processing. I'm going to focus on Sketchpad here because it's not only Turing's 100th birthday, it happens to be the 50th birthday of Sketchpad this year. And I'm sure Ivan has forgotten this because he's famous at forgetting things like this. And because he refuses to talk about Sketchpad, I thought I would say a few words about it. So it's famous for being the invention of interactive computer graphics. It's less known that it was really the first object-oriented system that had the abstraction technique of objects, masters and instances. You can make a master rivet and create instances from it. And the big knockout on Sketchpad was the programming of it was not done in terms of anything like a storage model, but was done by telling Sketchpad goals that you wanted it to achieve, and it had 3 problem solvers in it that would achieve those goals. And one of the famous examples here is this truss bridge. And it happens that there is no movie available of this truss bridge. And the reason is that TX2 took a while to settle the constraints on this bridge, I believe. But because it's the 50th anniversary of Sketchpad, we have recreated the Sketchpad display. And this twinkling, Ivan will recognize because it actually plotted points, and they had to be randomized throughout core. You go crazy with vertigo on it. And so with Sketchpad, you could add a truss in here. You could turn on the constraints, one of which is gravity. And Sketchpad would compute all of the beams there. And we can see what effect this one has of adding it in here. So this is 1962. Add a weight. Add another weight. And this twinkling and stuff caused a series of better displays to be made. But it's interesting that in many ways the semantics that are expressed here haven't been improved much on, although if we come into modern times we can make it look prettier. And we have this model is due to Yoshiki Oshima and Bert Freudenberg, who made this. And now in the modern version, of course, words have weight. So I'll say, Ivan, thanks. For inventing this. And we're doing the constraints a little bit differently here. And so we put them inside this weight here. Here's a couple of them. So here's the spring constraint. So the beams are all springs here. This is gravity. And this is the pin constraint. So if I turn gravity off, the springs will pull it. I love the idea, just the idea that a physical object is actually a process. So it's gone to 0. I'll turn gravity back on. And let's turn off the pin constraint. Now, the pin constraint is what is holding all of these girders together at the joints here. So just pull it off. Okay, but we have all these useful objects down there. And we know these objects, what we're seeing there are just costumes on these objects, so let's repurpose them. We'll give this system a different set of constraints, and I'll use the little balloon here to raise them up. Okay, and this is not such a big news because we do our layout using constraints. So this is a user interface of the system I'm actually giving this talk in terms of. Steve Jobs might like the steel look, but I think being a little more colorful, we can try a blue look here. That looks a little bit too much like a company we're all familiar with. So this system is a bit of a Frankenstein monster, so I'll go for a Halloween theme here. And I've got this is kind of like a presentation system, except I can program in it. So what I'm gonna do here is just go to the sort of the slide presentation, but in fact I can still interact with it because this is just a view. There are no modes in this system. And this brings us to what I think of as the third Turing machine. We talked about the first two. The third Turing machine was the machines he built out of biology. And this is, in fact, the first Turing paper I wrote, that I read when I was a biologist, was the morphogenesis paper. And even though I was a math major also at that time, I'll confess I did not understand the mathematics in it. It was deep. And actually he warns in the beginning of that paper of what parts to read unless you're really into mathematics. But one of the ideas here is he was trying to show that relatively simple systems of gradients interacting with each other can give rise to an enormous number of morphological structures. And these are some from his original paper, and these are computer generation of some of his models more recently. And you can do other things with these. So gradients, we can do something that's kind of like particles and fields. Here we got little ants following the gradient, and they'll all eventually migrate their way up into that upper left-hand corner. And it looks like they're somewhat coordinated, but in fact they're all just following their own thing. And even though we could build our text handling stuff in this form, it suggests, yeah, well, why not make the letters ants? And so if we tell these guys to interact with each other, and by the way, these three rules here are the rules for this text editor here, so you can sort of see what that looks like. And another little wrinkle in here, that was done by Ted Kaler. Another wrinkle here was done by Aaron Lunzer. And it's that nowadays we have the computing power so that we don't have to compute just one version of something, but we can compute multiple versions. So for instance, here are three suggestions, three views of this paragraph computed all at once in different worlds. And we see the outline superposed over it, and we can sort of see how this works. And this underlines that when you're doing what type programming, you really want to have a user interface that is giving you a sense of what the possibilities are going on, because the system is doing more for you than when you're doing sequential programming. And of course, there's the question of doing the graphics here. And so Dan Amelang did the graphics for this system, and in a similar way, using mathematical relationships first. Here's a formula for the involvement of a polygon with a pixel, and then he made a mathematical language that allows us to express that in a form that runs. So you can think of this as kind of a specification that actually runs. And in light of the previous discussions, I'd say my prejudices are to make our specification language something that we can debug and then ship. Because the problem is you're always involved in not just programming something, but you also have to do all the reasons for the programming, and those can have bugs also. So I kind of like this way. But I happen to agree with Butler that sometimes trying to make things clean is difficult. But on the other hand, think of how wonderful it is when you can make them clean. So that does things like that. And then we have a zillion compositing rules. But there they all are, just 95 lines of code. We have pen stroking and like this. And we have gradients and texturing and stuff. And the best way to show that is to go back here. And I'll just pick something in the user interface because the whole system is live. I'll say, OK, gradient fill. And now I'll just recustomize my little thing here because that's the live thing that goes along with that. Okay, and then back up, and then bitmap filters and everything. And so in this form, all of the 2D graphics that we're familiar with on a personal computer is 435 lines of code. And yeah, you have to learn a language. It's a little bit like APL meets Christopher Strachey. But in fact, the compactness of it and the understandability of it is fantastic. And in order to make languages like that fast, we made a meta language. Alex Worth did this, and it converts expressions into object relationships that you can do things like compile with or interpret, or you can do something really interesting and illuminating with it, as Brett Victor, young, fantastic user interface designer, Brett would say, that's not really interaction. You need to continuously experience the meaning of your meanings, not just hit buttons and have them happen. And this is possible in this graphics language because it's actually a data flow system as well as a very higher level language. And so the So here's an example of the letter D. And here's what Brett has done. He has automatically gone through that code that I showed you, and he has built this visualization over here automatically from it. So here's a Bezier curve, and I can edit this letter D here, and you notice everything else is reacting. Here are the 6 Beziers. That becomes the input of the rasterizer. That produces 49 span coverages. And I can come down here and I can ask, where did this pixel come from? I can open these up. And what it does is it takes me on a tour automatically through the code forwards and backwards and shows me what's going on. And of course, the next step after this would be, instead of writing this stuff over on the right first, you might want to start off with your examples first and develop the stuff on the right. Okay, and so an architecture for this is somewhat similar to things that have been talked about for a while. This is Alan Borning and Hessam Samini, who have been working on this. And basic idea is whenever you can stay up at the what level, the constraint level, the meaning level, the relational level, things are generally good. And you'd like to have a language or two, not too many of them, that really allows you to express these, not just for special cases. I mean, one of the points of this is it's time to start thinking of doing what programming for systems programming, making operating systems and basic elements out of it, where the system is in charge of doing the hows, the solvers, the optimizations, the pragmatics. And there's zillions of these. We want to work up here. And this is kind of Sketchpad-like. Sketchpad had 3 of these. We actually need a lot of them. And in between, we need something that is not just a kind of a chooser, but also kind of an expert system that knows about this idea, that can make judicious choices and maybe even parallel choices to tie this together. So when I look out on the world here, and somebody asks me about the Turing Tarpit, I think it's a Turing opportunity. And if there's a tar pit around, I think it's inside of our own heads. Thank you very much. Thank you.
Great. So we'll take questions. You point at someone and I'll run a mic to them. And we have about 5 minutes for questions. Questions?
By the way, I'm always very grateful. Butler always reminds me that Butler gives great talks and he actually gets done when he's supposed to. And I'm just grateful that he went on before, because he reminded me I should get done.
Good. Alex Wolf.
Hi, Alex Wolf. Aren't yesterday's what's today's how's ad infinitum?
I didn't catch.
Aren't yesterday's what's today's how's ad infinitum?
What was that?
I'm going to let Alan repeat it
It's hard to
again.
hear up here.
Okay.
Try saying it again.
Right. The point is that we don't know how to do something. We then know how to do it.
Oh yeah, I got it.
And then we complain about it.
Yes. Well, actually, some people even regarded Fortran as an AI program back then because it did something that only humans could do, and people used to complain that every time a problem gets solved, it's removed from the domain of AI. AI never gets any credit for it because it just goes into engineering. Yeah, there's something to be said about that, and maybe one way of looking at this is saying, hey, it's not that people haven't been working on what's for 50 or 60 years, but I think it's way out of balance if you look at where the programming is going, and I believe that the time is ripe now, over the next 5 to 8 years, to actually do something serious at this level that is sort of in between specifications, requirements, prototyping, and making something that can be delivered with perhaps by adding optimizations that don't get into the meaningful part of the thing. That's why this is a pep talk. It's saying, come on, funders, start funding the next revolution in being able to do serious programming, not just special case programming.
Okay, so there's a question over here. We're good. So tell us who you are.
My name's Ken Peer. Alan, I'm surrounded by Dynabooks. Got a little one in my hand.
It's too small.
It's been 40 years, and we've been talking all day about predictions. What are yours?
Well, the easiest, there's a saying that will go on my tombstone, but if you think about it, the easiest way to predict the future is to prevent it. So one of the ways of looking at today is the discouraging amount of stuff that's still around that was barely scaling when it was invented. So it's easy to predict that a lot of that will be around. Real question, I think in the experience of many of us, it takes critical masses of different kinds of people funded well to actually make serious breakthroughs, because ideas are not enough. There are plenty of good ideas around, but I came greatly to appreciate the qualities of people who can turn ideas into reality. And so it's really the combination of them. This is what is so difficult, for instance, from NSF funding, is funding projects large enough to do the engineering aspects as well as the ideational aspects.
Good. We're going to squeeze in one last question. How about something from over here? God, what a bunch of wimps. Nobody's got a hand up there.
There.
Oh, okay. I'll be right there. Put your hand up again. Ah, good. And tell us who you are.
Simoncuskey from Citrus Leaf. Alan, you talked about preventing, and you showed us this nice WYSIWYG live, very few lines of code. Now, the things that Ken was just talking about all his dire botnets, can you imagine using those techniques to deal with things once it gets out of your screen and starts going into the real world where there's spam and malware and adversaries?
Yeah, well, I'm always accused of being too optimistic, but To me, many of the protection aspects of things, I have probably an oversimplistic way of thinking about it, but I believe you have to do the safety and protection aspects as the first part of the design rather than trying to tack them on afterwards. And I happen to like the internet a lot. I think those guys did a fantastic job. And to me, it's the only real object-oriented system on the planet, because the machines themselves are the encapsulated things, and it is not possible to send a message on the internet that will cause any machine to crash. Because it's true, because it's only stupid software that other people put on the machine interpreting what is a pure message, interpreting that in some stupid way that allows that. So to me, the internet is a good model, and it must have a few billion nodes by now. It has never had to be stopped, to be updated. It's probably exchanged out most of its atoms and much of its bits at least once since, say, the late 60s when the ARPANET started. So it's the thing that is like a living organism. It's the thing that is going into the future. It's the thing that we have to look at when we're thinking about building systems. And so in a biological system, the entire dynamic in biology is not being correct, but in curtailing error. A lot of the proteins, maybe a third of the 10,000 proteins we have in each cell, are there just to correct various kinds of damage to DNA and other important molecules that are caused by kinetic energy of heat and some carcinogens. And so it's not a question of the thing being perfect. It's like the internet. It's not just IP, but it's having something like TCP that can make sure the retransmissions and other things happen so you eventually get the bits that you want, but you may not get them for a while. So it becomes a kind of a stochastic computing, and I think that it couples well to what Butler was saying, and also this model I was showing, that it's the more we get into the what's, the more we can build systems that can do these stochastic convergent strategies that will allow us to build bigger systems. Done?
On that very optimistic note, thank you so much,
Thank
Alan.
you.